Hey, John here. Let's talk about virtual memory and how it works, okay? Starting with the reason we need it, all right? So keep this in mind as we go so it'll make sense why we even do this in the first place. We use it to prevent one process from accessing the memory that's being used by a different process, right? We use it for security, plain and simple. What are the other reasons? Well, one of the other reasons is it allows a process to use more memory than you actually have in your home machine, which is kind of cool, right? You can actually run a program that needs more memory than you actually have. Or you can run many processes that, when all combined, are trying to use more memory than your machine has, all right? So you can oversubscribe to the amount of resources that are available in your computer, all right? This is pretty cool. All right, let's jump around a little bit so we can get some terminology in and then look at the example that I want to work out for you here, okay? So let's start with this. Let's say we have a core in a CPU somewhere, all right? We know that cores have things like, the register file, ALU, right? And those kind of go around in a loop like this. You got a program counter in there and maybe a finite state machine that orchestrates the control of everything, right? We can also have a thing called a memory management unit. All right. This thing sits between all the stuff that we already know about that's in a core and the memory. It manages the memory, plain and simple. So, what's going on with that? So let's go explode this view here. The MMU has like an input and it has an output, so let's just like expand that up a little bit. MMU, I need a little more space for this, right? So what's going on in here? This is what we call the virtual address. This is the physical address. So what happens is, anytime this core wants to talk to memory, the address that it wants to write into or read from, rather than just being connected directly to the memory, it goes to the MMU. That is what we call the virtual address. The MMU has the option to translate it to some other value and create what we call the physical address. And as you can see, this only concerns the address portion of the memory bus. So if we break that into two pieces, right? So there's the address bus, and then you have the data bus like this. Right? Usually that's bidirectional. Address is one way, right? The memory doesn't tell the core what address is being used. The core tells the memory what address to use, right? So there's the arrowhead there. And there's also a control bus of some kind. That has to do with, hey, I want to read, I want to write. Obviously, the memory needs to know which way the data is flowing, right? So you're going to have an address bus, a data bus, and a control bus. Combined together, we refer to that as the memory bus, okay? Memory bus is a bus of buses. Now let's think about some hypothetical CPU, right? That has, say, a 32-bit address bus, right? So that means this is going to be 32 bits, right? A little arrow, a little slash on there means there's 32 signals in that bus, right? Maybe the data bus is also 32 bits, okay? So if the address bus has 32 bits, how many total bytes of memory could there be? That's 4 gigabytes, right? Why? Because that's rounding off. It's a little more than 4 gig. It's 2 to the 32nd power. All right? So what happens if we have a 64-bit machine, right? Most modern PCs, even your phone, probably has a 64-bit address bus in there nowadays. How big is that one? Well, that's 4 billion squared, which is about 18 exabytes. All right? Go look it up. You got mega, giga, tera, peta, exa. This is really big, okay? Now, I'm not going to go into translating all 64 bits. Even 32 bits is a little excessive for a simple walkthrough that I'm giving you here, right? I'm just saying when you need to apply what I'm telling you to a larger address bus, it's just more of the same, Okay, so let's not worry about this. Let's stay focused on the relatively manageable size, which is a 32-bit address bus. So, quick review of what our memory map looks like when our processes are running, right? You got your text, data, BSS, your heap, and your stack. All right. 2 reasons that we need virtual memory. Right? Prevent one process from accessing memory that's in use by another, and allow a process or a set of processes to use more memory than we actually have. Okay? Now, what does that mean over here? If this is just one process, let's call this one process 0. Okay? How much memory is all this stuff? Okay? Let's keep it simple. Let's say there's 4 kbytes for each one of these, at least when the program starts. And you'll see why in a minute. This will work out real easy for us, all right? As we move these to different sizes, everything gets more complicated. So let's just make each one of these 4K. And let's further define a concept called a page, all right? Let's define a page as a block of memory and what we're going to do is we're going to design a system that allocates memory in blocks, each of which are the same size. And we're going to call that the page size. And in this example, the page size is going to be 4K. So, how many pages is there in the text region? 1. One 4K page for this example. 1 4K page for the data, 1 4K page for the BSS, 1 4K page right now for the heap. It could grow into more pages. If it grows to 8K, then it would need another page. It would be 2 pages. Same thing with the stack. When we're starting the program, we're going to just put 4K up here, 4K bytes of memory. 1 page will be allocated for the size of the stack. All memory allocations will be done in units, integral sizes of the page. All right, the whole machine is going to be based on its page size, and this is given when the architecture is designed for any given silicon. All right, some systems, yes, have variable sized pages. That's an optimization. I'm not going to get into optimizations here. We're going to do the good old-fashioned, tried and true, everything as a unit of fixed pages as specified by the hardware designer. And I'm going to say for our hypothetical computer, the page size is going to be 4K. This, by the way, is a pretty common size today. So how many pages, then, are in a machine with 4 gigs of memory? How many pages? Well, that would be 4 gig divided by 4K, which equals 1 million. I'm going to put approximately, all right? Because these are decimal values, and we know these are always in binary, and there's some rounding going on here. On the order of 1 million pages are needed at 4K each to describe a 4 gigabyte address space. How many pages do I need for this? I would need 4 billion million pages. That's a lot of pages. That's why I'm not going to draw a diagram with that many in it, okay? I'm not going to even draw a diagram with this many, okay? But there's no need to expand it out to this. This is just freaking huge, all right? And you'll see the reason I keep throwing this back at you is this needs to be optimized, all right? And I'm not going to get into the details of the optimization. And I'll close with how they go about optimizing it, but I'm not going to go into the details, all right? All right, so let's look at how the security aspect of this thing works, all right? So let's say I have a process 0, and he's got his usual stuff going on in here. Again, we're going to keep this small. Text, data, BSS, heap, stack. He grows down, he grows up, blah, blah, blah. All right, how many pages am I going to have in each one of these? For the purposes of this specific example, I'm going to have one page in each one of these regions, all right? This is going to get enough arrows in it as it is. If we have more pages, it'll get uglier. We'll add a page in a minute. Okay, then we have process 1 over here. I'll draw it right like this. Hopefully I got enough margin there. Stack. And he's got a heap. He's got his BSS, data, and text. Right? There we go. And let's say this guy has one page right now in use in each one of these regions. So what's going on here? If this is a 32-bit address space, each one of these, okay, we can start the text at address 0. That's a 32-bit address whose value is 0. The stack would end like this, all right? Now, does it really need to go at 0? No, you could put it wherever you want. But in order to keep as much space as possible available for the stack to grow as big as it could be, and for the heap to grow also as big as it can be, you don't want to waste memory around here. So what you really want to do is move these things apart as far as they can go to make this hole as big as possible so they have room to grow. That's all right? So what happens with this guy here and this guy here? Well, he also, I don't have it on a room. I'm going to abbreviate the addresses here, right? So this guy is going to be O followed by O, and then it's going to go all the way up to here to F, right? F as well. This virtual address space, okay? As opposed to just an address space or a physical one. Okay, this is going to go from 0 to all Fs, and this one's going to go from 0 to all Fs as well. Right? And these are virtual address spaces, okay? Virtual addresses are the addresses that your running program and all your pointers, every address you've ever thought of until today is a virtual address, okay? If you're running on a machine that has virtual memory, okay? All the user programs use virtual addresses for everything. It's only the operating system that starts worrying about the physical addresses, and or very specialized cases where a specific program could be written to say, I really need to have this physical address mapped for some reason, which usually gets into user mode, IO drivers, and things like that, okay? If you know what those are. If you don't, then don't worry about it. So how then do these things relate to what the physical address space is of the machine? All right. These are virtual. What's in here, the physical, the real, the actual memory. How does that get used? All right. Let's draw another table in here. All right. Now, obviously, if this guy's program is running and he has the code starting at address 0, and this program over here is running and his code starts at address 0, the bytes that represent this executable code in the text region of this guy's process can't be stored at the same place that this guy's is at. So what happens is, when the operating system is told, hey, start running process 1, he goes, all right, I need to go out into disk and I need to read in the text and the data and then zero out the BSS. Set the program counter to the beginning of the text region. Start this thing going. All right. Now, where in the actual real memory of the machine does all this go? Since obviously it can't go at real address 0 if this one over here is at real address 0. It turns out neither of them actually might even ultimately be at real address 0. So what the operating system does is you can sort of think of this as random. There's, a rhyme and reason to what the operating system does, but it's going to do whatever's optimal for however the operating system was designed. As far as we're concerned, it goes in whatever memory is currently available right now. Okay? So let's say it needs to read in the text and the data from disk. Where does it go? Well, let's say there's, memory that is in use for some reason. The operating system itself might use the lower part of the actual address space. So let's say these 2 pages down here of physical memory are currently in use by the operating system. All right. And that's not unusual, by the way. The real physical address space down low and down high is almost always in use by the operating system and I/O devices and all kinds of physical things to do with the machine. All right, it's usually the middle part of the actual real memory that is available to be allocated in the way I'm going to talk about here to these running processes. Okay, but where it is we'll see, is not relevant at all. So what happens? So let's call this text 0, data 0, BSS 0, heap 0, stack 0. Oops, this is process 1. It might have been a good idea to call that stack 1, heap 1, and so on. Not a good idea. And these are going to be zeros, okay? All right, just so that we can differentiate between the two when I draw it inside here, okay? So he wants to read in 8K. What he's going to do is, hey, this page over here looks like it's available right now. So he's going to put text 0 right here. And then, as we're going to see in a minute, he's going to map this so that when this process, geez, I keep doing this wrong, text 1, when this process number 1 is running, and that process wants to read from memory address 0, okay, these are 4K pages, remember, which means this range of addresses will go from all zeros to what? 4K would be 0, F, 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 right? This page here would start at all zeros followed by 1, 0, 0, 0, and go up to all zeros followed by 1, F, 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 right? And this would be at 2, O, O, O through 2, F, 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 and so on. Because each one of these 4K pages in decimal is 1,000 in hex, all right? So that's what's going to happen in here. Same thing here. It'll be 3, O, O, O to 3, F, 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 right? And this stack here will go from what? F, 0, 0, 0 to F, 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 like that, all right? One page for each one of these. So there's this mapping going on. Maybe it says, okay, his data region for process 1, data 1, for whatever reason, the operating system sees fit to put it right there. So he has to say, all right, I got to remember it's right there. What about his BSS? Well, remember, the BSS is just a page of zeroed out memory. In this case, it's not just one. In this case, they're all one page, so the BSS has to go somewhere. Maybe OS decides to put it there. Oh, he has to remember it's right there. What about the heap? Well, the heap for that could go over here. It's BSS1. Heap 1 might go right here. Remember that that is stored in there. Okay? Stack, stack. 1 is a page. Remember that. This mapping is what we're going to get into here. That's the whole ball game. All right? This is what the MMU does, the Memory Management Unit. What it does is it translates these virtual memory addresses to physical memory addresses, right? Right? And the process of doing this is called dynamic address translation. Okay? Now, the way it does this is it just builds a table that holds all these mappings, okay? For this process, it has a single table. It's called the page table, in fact, because it maps all these pages of virtual space to all these pages or wherever they belong in physical space. This process over here, where does all of its parts go? Well, maybe its text 0 goes down here. Maybe its data 0 goes right here. As we can see, it doesn't matter where they go. As long as somebody says, when you need to access any bytes between right? What are the address range of this data section? Well, it turns out since they're the same, it's going to be this. This is from 1000 in hex to 1 FFF in hex. If it's in this range here, translate it to look over here, wherever that might be, completely different place in the physical space, right? Clearly, it's not at 1000 in hex, which is where this second page really is, right? 000, and this would be at 2000, and this one's at 3000, the beginning address, right? And this one is at F000, right? Oh, F000, okay? The same kind of thing that you see over here. All right. Well, where's this one at? Well, it doesn't really matter. This would be 0, 1, 2, 3, 4, 5, 6, 7 in this example. If each one of these is one page, it would be at 7000 in the physical address space. All right. This heap one here would be at 8000, right? This would be 6000. Each one of these is a 4K page. 5000, 4000, 3000. Hopefully I counted it out right. 2000, 1000. I missed one of them. And 000. All right. These are the physical page addresses. This process zeros virtual addresses, right? So anytime this process wants to look at any of the values of data 0, it has to go find it in the physical memory over here, starting at 7000. So there's this mapping is the whole point here, right? So each one of these are going to go to different places. Maybe his heap is up here. Maybe his stack maps over to here, okay? How then do the mappings take place? First of all, we need to note that this process has its own mapping that's completely independent and unrelated to, in every way, shape, or form, the mapping of this process over here. Okay, so each one of them has its own mapping. The mapping is done by what's called a page. It looks up and does the translation by using what's called a page table. So let's look and see how these page tables work. I'll keep this picture handy because we may have to refer back to it. All right, so I'll just put it right up there. Let's look and see how these page tables work. Right, so process 0. Okay. Process 0 is this one, remember. It has 1, 2, 3, 4, 5 pages that mean something in its address space out of the approximately million total pages that a machine with 32-bit addresses would have, okay? So how many then translations could there be in one page table? All right? Well, that's the million. Approximately 1 million entries. Oops. Okay. So this is just an array. And the page number is used as the index for this array, all right, in this table. So if I want to know where page 0 is in the real memory, in the physical memory, okay, I'm going to create a table whose element number 0 has a value in it that is 3000 or 2000 in hex, 2000, right? 0, 1, 2, followed by 3 zeros. That's the beginning address of where this page is in physical memory that corresponds to page number 0 in this process's virtual address space, okay? So where does virtual page number 0 exist in the real memory? Well, that is at 2000, okay? So I'm going to use this table to just look them up. Anytime this process reads from memory, the MMU will look at the first 5 digits of the address, because if you think about it, that of the hex value, right? That's the page number. The last 3 digits over here is what we call the page offset. All right. So let's look at that. Let's break that down. Is what? So let's take an arbitrary page whose virtual address is 1, 2, 3, 4, 5, 6, 7, and 8. All right, so we don't confuse these digits. These digits here in hex in this hypothetical machine is the page number. The last 3 digits over here is the page offset. This is true for all processes in this hypothetical machine, all right, and all page tables. So this page number, 5-digit hex number, all the values could be between all zeros and all Fs, right? For a 5-digit hex number only, right? That means that I'm going to have a million, right? F, 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 F in hex is on the order of 1 million in decimal, okay? So if we use hex addresses over here, because I don't want to do the conversion in my head, page table entry number 0 for page number 0 maps to physical address 2000, right? Or does page number 1 map? Well, that would be 00001,000. Okay, where does that go? Well, he goes over here and he starts at address 7000. All right. Well, I left out the leading zeros. All right, 000. Okay. Well, where does page number 2 go for process 0? Well, process 0, here's a page number 2, and it's over here, and it goes somewhere. Let's say that one goes to F000, all right? And let's say the heap is mapped at, 20000, okay? If that was the case, that F000 would go here, okay? And this page number 3 up here to 200000, right? 200000. Right? What do we do about all these other ones? Well, there's no pages in there. It's not using this memory, okay? Everything between here and here is not in use. And this is where we get to the part about we're actually going to be able to use more memory than the machine actually has, all right? So this thing thinks it has 4 gig, but it's never going to touch this. So, yeah, if it never touches it, we don't actually need to map it, okay? So what do? Well, of the million total entries in this table, we just mark this as invalid, 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 invalid. All these are invalid till you get to something that you have to map again, like this one here, which is, this is the page number of this last one, right? It's F000. I should have done it for process 1, actually. So here's the address of where the stack starts, and this is, remember, the page number is the first 5 digits, okay? So for this one, whose stack is also at the last page and at this same address, right? He maps somewhere. Maybe he goes to 3F000, all right? So in here, it will be 003F000. I missed a digit there. There'll be another 0 over there, right? Because his page number, FFFF, really needs to be translated to page number 003F in order for this mapping to work out. Okay, now, of course, this is not to scale, right? I'll put ... up here for all the rest of the physical space, right? There's an enormous, this is, relatively speaking, enormously bigger than the rest of this drawing here, okay? As is this. Remember, there's 1 million entries in here. This is about 1 million plus, 5, right? So there's 5 in use and almost 1 million that are not in use. This is a big ... right here, okay? I'll keep that in mind. Oh, let's look at what happens with process number 1 over here. How does that guy work? Well, we make a page table for that one. All right, what observations can we make? Well, the pages for process 1 should not be in the physical memory in the same addresses of the pages of process 0. Otherwise, we got a problem, okay? I mean, it just should make sense, right? That's how the security part of this thing works. So if we got process number 1, its text is at, what is that, 3000, okay? With its page number 0. is mapped to this address over here. So its table would look just like the other one, but they would all map differently, right? So it's a page 0, 1, 2, 3, ... and 1, 2, 3, 4, 5. F's is the last one. So what did I say? His address 0 in his virtual address space, the page of data that's stored in there is really at 3000. Now notice that every one of these ends in a 000. As an optimization, we don't need to store the 000 because no matter what, all the values end in 000. And it's just a waste of memory to store all that extra stuff when we know they're always going to be 0. So the real value that's stored in here is just the page number itself without those trailing zeros. So that would actually be the 3. Okay? Without the trailing zeros. So you could say 00003. Why? Because it's just the page number and the physical page number for the virtual page number 0. Virtual page number 1 at 1,000,000 is remapped over here to 6,000,000. So this virtual page 1 is mapped to physical page number 6. All right. So that's 00006. All right. What about the next one? Virtual page number 2 is mapped over here to physical page number 5. 00005. Next, virtual page 3, physical page 8. 00008, and so on. All these would be marked invalid because nothing in here is currently in use, right? The stack here, whose page number is FFFFF, is really at physical address page number 20 in hex. So that means 20 what with 000 right here, okay? So, and again, all this stuff is invalid. The bulk of this table represents illegal pages, all right? And we'll see how you get rid of all this with this wasted space in a minute. So, these tables are what do all these mappings here. These things are called page tables. Each one of the entries in a page table is a page table entry, okay? I'll write that sideways. All right, one other piece of terminology there. Each page table entry can either be valid and point to a physical page in the actual real memory, or it can be marked as invalid and not mapped anywhere. Okay? All right, so let's watch these processes run. When this process runs, program counter starts off at 0 or some known place, wherever the text is. That's all dependent on how the operating system is designed and beyond the scope of this discussion, and quite honestly, quite irrelevant. It's somewhere, right? And by convention, it will do whatever it's going to do. Quite often, it just goes to the first instruction in the text region, okay? And it'll just start executing code. So if there's an instruction in here that says read some value from memory in the data region, it'll be reading the value from the data region in these range of addresses here. These are all the virtual addresses. Like I said earlier, when your program runs, every address that you use, every pointer, every register value, everything that has anything to do with your running process is all virtual. And the CPU itself, which is part of a core inside of the CPU, right, has this MMU in it, and it's constantly converting virtual addresses to physical addresses in order to do this remapping that constantly takes place, the dynamic address translation, okay? So as this program runs, it is none the wiser and everything works perfectly. If I start another process number 2, I start using pages in here and maybe some up here or up on the top. And he gets his own page table. I can run as many processes as I want, as long as I have enough room to hold all those page tables. All right. Now, let's say this process is going along and it reads a value from some memory address that's in this region in here. Maybe it wants to talk to something at 8000000. What happens? Well, process one's page table, right? Well, what's the page number for this thing? It's this, right? It's the most significant 5 hex digits, 8 followed by 4 zeros. Well, the MMU is what uses this page table, and it goes and sees, okay, what happens for page 80000, right? It sees it's marked as invalid. If you ever do this in a running program, that's what causes a seg fault, all right? That is the definition of a seg fault, all right? You access something that you're not supposed to touch. You're allowed to touch anything in these pages, this page up here, but nothing allowed in here, okay? Now, what if, while your program runs, you want more heap space? You know, you just did a new, I want to create some objects. I need some more heap in here, all right? Well, you need to move this line up, okay? And as we will see, this is actually called the BRK. And there's an actual function inside, you know, on Unix system called like sbrk. Set the break line. That's what that SBRK, SBRK. And it says move it up, or I can move it down too. If I have a lot of memory and I want to free it up, I can start moving it down. I start deleting objects, okay? I need to be able to move this thing around. So what do you suppose that function really does? What happens is it goes and tells the operating system, move this up here. Thank you very much. And if it moves it out of this page, all right, up really high, the OS might need to allocate one or more pages so that the program continue running, all right? So if it does that, let's say it needs one more page. Well, it will no longer be invalid anymore. That would be page number 4, right? By definition, this heap right now is sitting here at the page number 3. And if I want to move it up and add one more page, let's say, that means pages 3 and 4 need to be allocated to the heap. So it goes and looks over here and finds an unused page. Maybe there's one right here. And maybe the address of this page is, you know, C000. All right. Well, what page number is that one? That's page number C. It puts it in this page table for process number 1. It no longer marks this invalid bit over here. And it returns from sbrk. The line's up here now. So now the running process can start talking and interacting with memory in here without getting a seg fault, okay? That's how that works, okay? You ever touch anything up here beyond the end of the heap and between the heap and the stack, you're going to get a fault, all right? Now, sometimes it's called a page fault. It's literally a page fault in this scenario when you're working at this low level. We're talking about a page that is illegal, all right? A segment fault is a convention for other, it's more of a traditional word because they used to have things called segments, and then they broke segments into pages. That's part of the optimization I don't really want to talk about, okay? So as far as our terminology goes, a seg fault is the same thing as a page fault, all right? At least in the scope of this discussion. So you can move this thing up and down is my point there. How does the stack ever grow? You don't actually write subroutine calls that say, please move my stack line down. No, that doesn't work that way. That has to happen automatically. And the way that does it is that if the CPU sees you poking around in memory up here near the top of the stack, it'll go, well, it's not like you moved all the way down here, right? I mean, that's 2 gigabytes away from the current stack up here, okay? This is a halfway mark through your memory, all right? You're nowhere near the heap, and you're nowhere near the stack. This is 2 gigs. So it knows you blew it. But if you start interacting with something near the top of the stack, it says, he probably just overran the one page that's up here. Let's allocate another one, right? So this thing came down, so let's throw it. Let's move that one down here, and this is like automatically done, right? So maybe he needs another page for that one. He puts it in here, and maybe that's a 10000. Okay, so he grabs another page in there. So what does he do? He says, make this valid. And now we got 10 for the page number, followed by 3 zeros again. All these are being optimized away. This one has all the address digits in them, but they never store these. If you actually look up how this works for any CPU anywhere, you'll see they don't store all these zeros. It's just a waste of memory. Okay. So what's the point? The stack then just grew. You have another valid page, and the other ones in here are still invalid. All right. This is the nature of a running program. Plain and simple. You manually move the pointer to the Burke line up and down to grow the heap in this direction here. Now, notice this is a 0 up here and all F is down there. This one's drawn with a 0 down here and all F up there. I'm sorry. These things get flipped up and down all the time in all the documentation. Some systems are one way, some are another way. I'm sorry to flip these tables upside down, but when I think of arrays, I think of the indexes going from 0 to whatever in this order. And when I think of memory, I think of the low addresses, low on the page and the high on the high of the page. All right, so just bear with me here. Keep your wits about you. This is 0 through FFF, and this is 0 through FFF here, okay? Just flip it upside down. Maybe turn your video monitor over if necessary. All right, so back to our top list here. How do we keep these things apart for security reasons? Well, that's easy. Don't map any of the pages in this table to the physical pages that are the same as the physical pages that are mapped over here. That way, it's not possible for this process to touch any of the bytes that are being used by this process over here and vice versa. Okay, that's how the security works. Now, how do you actually say use more memory than the whole machine has? Okay, for real. All right, well, this is kind of faking it. I just mark all these as invalid and pretend like there's memory way up at the high addresses here and the low addresses down here. And same thing for this other process over there. But what happens when I really do run out of memory? Let's say I'm running 500 processes, and they all have big heaps and big stacks, and they're all using all kinds of memory, and I run out. Well, in that scenario, okay, say we have, process 0, process 1, process 2, process, 50, 60, even with 2 processes, or even with 1 process. In theory, you could try to use more memory than you really have, right? In this case, if I really do have 4 gigs, and I'm only running 1 process, then that situation cannot happen, because the most memory this would ever need is 4 gigs. And if I really have 4 gigs, I can't really run out. But if I had 2 processes that each want 4 gig, now I got a problem, because each one can only have at most 2 gig. And that doesn't account for the memory that's in use by the operating system. So how do we deal with that? Well, what happens is, let's say I move this Burke up, huge distance. I want, 100 megabytes in here, and I don't have 100 megabytes right now. What happens? Well, 2 things happen. 1, the operating system can move the Burke line up here and just leave the table like this. Now, why would you want to do that? Well, it turns out you can mark all these as invalid, but then you could keep a flag in here as well that I'm going to put NR for not really, okay? So maybe a couple of pages up here are invalid, but not really, all right? What we call this scheme is demand paging, okay? Now what's going to happen is, and this is very common, by the way, sometimes it's very annoying when an operating system will do this. Linux does this. I don't know. I suspect that Mac OS does it as well as Windows as well. Because what happens is people become very complacent with writing programs that are incredibly wasteful when it comes to memory. Like web browsers are notorious for this sort of thing. And what they do is they say, I need, 100 megabytes of space, and then they never really use it. So what the operating system does is it lies and says, oh yeah, sure, you got it all. Yeah, right. Okay. And but it remembers that it lied to the process. All right. So later on, and the process is running, if it actually starts using this data up here that it asked for, if it uses it for real, then the operating system goes, oh no, because it'll start getting page faults. Because as far as the MMU is concerned, this is not allowed. Bang, get a page fault. And the way a page fault works is the CPU stops the program and it goes into the operating system and says, this program got a page fault, you deal with it. And the CPU is done at that point. So the operating system looks in here and says, oh, I didn't really allocate those, but I should have. And if the program got a page fault, say on this page right here, what the OS would do is it would say, all right, fine, I'll go find a page for real, and maybe it'll find one right here, and maybe its address is, I don't know, A000, okay? So it says, all right, I'll fill this one in, A, and I'll turn off the invalid bit and restart that program. That program can now use this memory. And it could run and do whatever it wants. And maybe eventually it would start using these other pages that it asked for, but the OS didn't really give it to it, all right? So this here is one way that a process can actually ask for a whole lot of memory. The operating system doesn't really give it that memory. It might not even have it to give, but it might say, okay, feel free to try and use it. And eventually, if the program actually fills all this up with data, each time, one page at a time, oh, now it's really using this one. Oh, now it's using that one. And it starts mapping them to all these little holes around the address space. It says, oh, he needs a page, he needs a page, he needs a page. He keeps filling those in, right? Eventually, the whole machine might run out of memory. Okay? It may run out of memory because it allowed a process to oversubscribe itself. It might be that we're starting more processes and none of them are oversubscribed and everybody's honest and they're only using a little bit of memory, but all those little bits add all up. But we've actually run out of physical memory for real. What do we do now? Well, let's say I start up process 3 at the point that this is running right now. And let's say right now, every single page of the physical memory is in use. There's nowhere to put process 3. How does that work? Well, the operating system can either say, no, I can't start any more processes right now because I'm out of resources, or it can steal pages away from running processes. How does that work? Well, let's say this process here has been running for a while, and I want to start up process number 2 or process number 3 and so on. And I need a page or a bunch of pages. What I can do is I can say, look, process 0 has been running a long time. I'm going to steal the page where his stack data is and take it away from this process. So what I'm going to do there is I'm going to copy that page to disk. I'm going to remember where it is, and I'm going to mark this as invalid, sort of like this, not really, but I'm going to mark it as paged out. There'd be like another flag in here. Whenever it's invalid, I could have other flags in here, like paged out, not really, whatever you want to do it, whatever you want to call it, right? So along with remembering it's been paged out, it also remembers where, right? What sector on the disk did I put that on so I can go find it later? Okay, so what happens here? I stole a page from a running process. I wrote it out to disk and I remembered where on the disk I put it. I mark it invalid and I set a flag that says this is invalid as far as the MMU is concerned, but as far as the operating system is concerned, if somebody tries to access this page down here, the process will die with a page fault. The operating system will go, oh, I stole it. I need to get it back. It would read it back in off the disk, put it somewhere in memory, not necessarily in the same place. In fact, odds are they never end up in the same place. It just has to go somewhere. Then it'll be remarked as valid, and the new page address of where it found it, wherever it found space to put it, it'll point to that new location. All right. Maybe it'll no longer be here. Maybe it'll be in a page down here. So maybe at that point, this will end up being down here at 4,000 in hex, okay? So we can steal pages away from running processes is my point, provided that we have enough disk to hold them all right? So this thing here, we call this paged out, right? And in order to do that, we need to have a big disk, right? Let's say we have a 1 terabyte disk. 1 terabyte, right? That is 1,000 gigabytes. And because our machine here has 4 gigabytes of memory, that means we can have 256 times more virtual memory in use at any one point in time than we actually have physical memory if we use this whole drive for what we call paging space. Okay? So the mechanism that the operating system uses to steal these pages away and store them over here and then bring them back later, this is called paging, right? Now, this is the modern version of something else called swapping. Okay, before we had virtual memory, what we used to do is take the entire process, the entire address space of a running process, and copy the whole thing out to disk, rather. And remember that we have done that so that we can run a different process. Okay, so this goes back to the early days. Nobody really swaps anymore. You can swap, but for the most part, it's only paging nowadays. If every single page is copied out to disk, you could still say, and you say that the whole process has been swapped out. But more often than not, some of the pages are in, some of them are out at any given time when a process is running. And you can check that anytime you want on your various operating systems by seeing how much real memory is in use and how much virtual memory is in use by using some of the system tools that they provide. For example, on a Linux system, you can just run this top command, all right? And what this shows me is a bunch of processes that are running right now. Like FFmpeg is running. That's actually what's recording this video. And we see the virtual memory, all right, that this process is using is this number over here. But the resident size, the amount of actual physical memory in use right now, is this number over here. Clearly, you can see that it has a lot more virtual memory in its address space than it does actual memory over here. Blender is the application I use for editing my videos. It's jumping around a lot here. Let me hit quit. We can look at this more closely. So 4.7 gigabytes. I don't remember the units of this thing, but it's probably in K. So that would be, what, 408 megs, 7 gigs virtual, and 4 gigs resident. Okay? Probably. This down here, what is this? The part of a web browser that's running. You can see this has got a couple orders of magnitude more virtual than physical, and so on. All right, this one's even worse. What's that thing? The GNOME shell. Yeah, that's the GUI running on the desktop right now. So anyway, and of course, Firefox, using a lot more virtual space than physical, right? Why? Because it's probably very actively using all the memory in the pages that are represented by this number of bytes, and it's not at all active, or it lied and said it needed a lot, but it never really used it, and the operating system said, sure, yeah, I'll let you have all this, but only if you actually touch it while I make the physical pages mapped to the virtual memory. Now, this is really all there is for the fundamentals of how virtual memory and paging works, okay? Now, what are some of the observations that we can make about this? How big is this page table? Well, it has 1 million entries, and each entry is 4 bytes long. This table, in its entirety, requires 4 megabytes of memory to just hold this table. That's kind of big. especially if you're running a process that only needs, a couple of K of memory. This thing is then, 1,000 times bigger than the actual memory it needs. This is not an efficient way to do this, okay? This one here would also be 4 megabytes total, all right? Now, as we've seen, this has a tendency to need more pages, starting at the highest page numbers coming down as the stack grows. And as the heap grows in the other direction. So you'll see pages starting, I need a page, just like you saw over here. Give me more pages for the heap. Going up this way. Give me more pages for the stack. The page numbers going down to allocate more space to the stack. So what happens is this space in here, which is this space in here, is huge. Well, remember, there's how many elements in here? There's 1 million elements in this array, and we're using 5. All right, that's not a good performance ratio. That's very wasteful. All right, so let's look at one of the optimizations that we can do in here. Right, well, just figuratively speaking, we can break this table up into a bunch of tables. Right, what if we had one table that's an index of 1,000 other tables? All right, you end up with a data structure that looks like a tree. All right, let's look really quick at this. We can call this a level 0 page table. It would have 1,000, or more accurately, exactly 1024 in decimal entries in it. If each one of these was a pointer to another table that had 1024 in it, right? Then that means there would be 1024 tables, each of which would have 1024 elements in them. That's 1 million elements. So what happens here is that this guy here would point to a table up here. These are level 1 page tables. And again, this all depends on vendor terminology and whether there's a 2-stage table lookup or a 3 or a 4, and however many elements there are in these tables radically depends on the different CPU vendors. And again, some of them are even variable length, okay? So just conceptually, I'm speaking here. Normally, there is a multi-table lookup scheme. All right, you don't have one big one. What you do is you have a whole lot of little ones, all right? In this case, there would be 1,000 little ones, all right? But we don't actually need all 1,000 of these little ones, because if we're going to run a process like this, we only need a couple of page table entries down, way up here at the end, and a couple of them down here at the beginning. All right, at the beginning of the virtual address space. We only need pages 0 through 3 and page, whatever this is, 1 million over here. So what we can do is we can say, look, the level 0 can also have an invalid bit in it. And if this only has 1,000 elements in it, each of which are 4 bytes, that's 4K in size. The first one would be valid and says, I'm a guy pointing at a level 1 table that has 1,000 elements in it. The last one is valid, and I point to a level 1 that has 1,000 elements in it too. This page here would map to the biggest one, if this is page, our segment number 0 through 1K in hex is 3FF, okay? Right, page number 1023, which would be the last one, is a member of the table over here. This table is the last 1,000 pages, okay? This would be invalid, 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 and down here we'd finally see valid in that address here. It's currently paged out in this scenario, but if it was valid, the 0003F would be right there in this table right here, okay? These first 4 would be at the beginning of this table. In this scenario, 1K, 1K, 1K. That's 3 kilobytes of memory to hold these tables in this 2-table scheme. And all these other ones are not even there. All right? So 1,022 tables are not even in the memory for this 2-level page translation table. All right? Modern CPUs have 3 and 4 levels, all right? And they have all kinds of different ways of doing this. So again, look up your specific vendor to see how it works, but conceptually, this is exactly what's going on in there. We use a multi-level scheme to save even more memory. This is all, at this point, this is just optimization. Conceptually, they all still do this. There's the idea of all the pages are described in some way. They're all either valid or invalid, and then the operating system keeps track of why they're invalid. Is it invalid because I said I'd give him a new page that doesn't have any data in it yet? Is it invalid because I stole it away and I need to sneak it back if he ever tries to access this? All right. And there's other reasons that this happens as well. Once reality sets in and things start getting complicated. Okay. But at the fundamental, most basic root of the whole thing, we simply take the page numbers that are in the virtual address and replace them with the numbers here. Okay? Physical page number here, virtual page number over there. All right? That's all there is to it. Thanks for watching. See you next time.